No, 113.
113?
Yeah.
Okay. Grams of Na2SO4.
0.6.
0.6. Oh, I was off. I'm going to do the same thing for the water. So 0.80 moles of H2SO4. This time I'm looking for water.
Wait, that's my question. We don't have to use the NaOH to find the water?
Good.
So you can use either one?
Can use either one.
Okay.
Everything is related, so I can use either one. So if I use the H2SO4, I have moles of H2SO4. The ratio here is 2 to 1. Now if I use the NaOH, the ratio would be 2 to 2. But you'll notice that the starting value would be different.
Gotcha, okay.
So I'm going to get the same answer here of 1.60 moles of water, and water is 18 grams for 1 mole, so
28.
of course 28 grams water.
Dr. Braun, can we please revisit the ratios when you were talking about if you do it with the H2SO4?
Sure. All I have to do is look at the equation.
See?
If I have water, H2SO4, I look at water and I look at H2SO4.
Okay. So in each one of these, we can just use the ratio.
I don't know exactly what your question means because you have to use the ratio if you're looking for something compared to something that you already have.
Right. Well,
It's
if
not a
you-
matter of could use it, it's a matter of we've got to use it.
Okay. We were solving it using the NaOH.
That's okay. That's perfectly all right. Then the ratios will change. But you still have to use a ratio that is connected to what you're using.
Okay.
So if we used, well, let's just do it. I have 1.60 mole of NaOH.
Mm-hmm.
Okay, I'm looking for water. I know NaOH. What's the ratio between these two?
2
to 2.
to 2.
2 to 2. So I get 1.60 mole of water. Looks remarkably similar. Same answer,
Okay.
which has to be the case. These two. Okay, anything else?
I'm actually having a hard time knowing like which side to use information from. Like, I don't know why it confuses me, but
There's no sides. You use the information from whatever side the thing is on that you need to do. So it's not a matter of picking sides, it's a matter of picking a component. So I know H2SO4, I want to know NaOH. I don't care where they are. I just find where they are and use their numbers. It doesn't matter whether they're reactants or products.
Number 2, is nitroglycerin decomposing to nitrogen gas, oxygen gas, and carbon dioxide and water. And it's asking how many grams of nitroglycerin are needed to produce 1 kilogram of carbon dioxide?
Right? Trouble?
Yes.
Okay. A kilogram isn't a conventional unit for us. What's more conventional for us? A gram. So can I convert a kilogram to a gram easily enough? How many? So I have 1,000 grams of CO2. First thing I'm going to do is change that to moles. So 1 mole of CO2 is 44 grams. So 44, 20, 27, 22.7 moles of CO2. And it wants to know how much nitroglycerin.
Yes, in grams.
So I take my 22.7 moles of CO2 and I'm looking for nitroglycerin. I know CO2. So I have to go to my balanced equation and I have to find out what the ratio is for nitroglycerin and carbon dioxide. Was that 4 to 10
4 to 12.
to 12? So that's a third, so this is 7.6 moles of nitroglycerin. And it wants grams. So now I have to multiply by the molecular mass of nitroglycerin, which is like 227 grams per mole. And we get 2158.
And I have to do it by
Can I remember that number? Maybe it's wrong.
172.
How much?
172.5.
No.
That thing says 17, right?
This number is 172?
No, the answer. Is that what you're asking me?
Yeah, 7 times 227's got to be more than 172. 1,725 grams of nitroglycerin. I'll buy that. Did you put in 0.76?
I did.
Okay. It's 7.6.
Oh, I'm so sorry. It's 227. Yeah.
Oh,
I put 22.7. I'm so sorry. I
Ah,
get it.
okay. So we're okay?
Yes.
Any others? All right, great. We're talking about liquids and solids. And we have worked our way up to something called the kinetic molecular theory of matter. In other words, we have a concept, a theory that kind of describes the way we think matter is composed and behaves. And so we want to describe that with several points, much like we did with Dalton's theory of atoms back in the day. We have a kinetic molecular theory that helps us to try to understand how substances actually interact with each other. So the first statement in our theory, our kinetic molecular theory, is that matter is composed of tiny particles called either atoms or molecules, depending upon what substance we're dealing with. So tiny little particles. 2, the particles are in constant motion, and therefore they possess kinetic energy. When anything has motion associated with it, it possesses kinetic energy. Kinetic energy is the energy of motion. And so these particles are in constant motion, and therefore they possess some kinetic energy. The particles can also possess potential energy as a result of attracting or repelling each other. There's going to be some mutual attraction or mutual repulsion, and this supplies some potential energy. 4th point, the average particle speed increases as the temperature increases, or the energy increases as the temperature increases. If we increase the temperature, we increase the speed. If we increase the speed, it increases the energy, because the energy is related to the velocity, to the speed of the molecule. So the hotter the sample, the faster the particles are moving. These particles, point number 5, collide with each other, and when they do, there's no energy lost in the collision. In other words, they're perfect collisions. The 2 particles come up against each other, bang, they bounce off of each other. Each retains the appropriate energy, and so there's no energy lost in the connection between the particles. So in a gas, these particles are in rapid motion, they're widely separated, and they're free to roam throughout the container without interference from each other. Now they do collide with each other, but the collisions are perfectly elastic, they bounce off of each other, go on their merry way. So they tend to ignore each other in that fashion. Now, how can I convince you of that? How can I take a sample of gas and convince you that the molecules are in constant motion and not just standing there looking out at us like we're sitting here in this classroom? How do we know they're moving? Can we see the molecules? We can't. We can't see them. So is there any experiment that you could think of that I might perform? Let's go back to our little blue bottle days in the laboratory and think about our experiment that we're performing. Can I do an experiment that would convince you gaseous molecules are in motion? What would you do?
Maybe put like a balloon or something and move it around.
Okay, but if I blow up a balloon and tie it with a string and put it on a stand here, Do you see the balloon moving around? If I tape it to the stand so I can't have any motion in the room. Is the balloon edges going like this? No. So that doesn't really prove that the molecules are moving inside the balloon. There are gases around it, but how do I know they're in motion? Colored gas, okay, so I put a colored gas in a jar, it totally fills the jar, and
I was thinking watching a colored gas dissipate.
now we're closer to it. That'd be a good idea. If I open the top of the bottle, if those gaseous particles were not in motion, what would they do? They would
Stay
just
inside.
stay there looking out at us like we're sitting in the room. Okay, but if they're in motion, some of them are now going to be able to escape. One other technique we often use is to use something like ammonia. Because what happens if you take the top off of a bottle of ammonia? People in the front row are going to detect this before people in the back row, but they're going to smell the ammonia. And the only way we could argue that is that the ammonia particles are leaving the bottle and entering your personal ammonia detector. Okay? And the fact that people in the back room would detect this later is more evidence for the fact that they're in motion, because they would have to move this way and they would come to the first people in the row rather than the people in the back row first. Anyway. Okay. Liquid molecules are also in motion. But now there are more important interactions between the particles so that they sort of stick closer to each other. Now, there again, let's talk about an experiment. Here's a bottle of water. My statement is that those water particles are in constant motion, banging into each other, banging into the walls of the bottle. How can I prove that to you? Poke a hole in it? Well, if I poke a hole in it, then they'll definitely move, but I'm saying they're moving now.
Heat it up.
How would heating it up convince you that they're moving now?
It would expand.
Do what? It did take up the shape of the container, but that was initially. Well, if I put sand in there, would it take on the shape of the container? Would it be moving around? Okay, so how do I convince you that they're moving around?
You shake it up.
Add some food coloring. If I put a drop of food coloring in it, if those particles are not moving around, what would the food coloring do? Blah. It would stay right where I dropped it. But what does happen to the food coloring if you put a drop into a beaker of still water? It will spread, and given time, it will spread uniformly throughout the sample. And the only way we can explain that is to say the particles are in constant motion with respect to each other, and mixing will occur inevitably. Solid particles, on the other hand, are held in fixed positions. Their shape does not change. If I have a sugar cube, for example, those particles, or the sand, we could take the sand in the bottle. We put those particles in there. If you recognize one particle by its shape or its color, you came in the next day and no one had touched that bottle, would that particle be in the same spot? Very likely to be in the same spot. Now, this gives us other properties associated with these physical states. Gases have low densities because the particles are very far apart from each other. And so the amount of matter in a particular volume is very small. They have indefinite shape, as we talked about before. They're very compressible. We can take gases and compress them down. Think about this in terms of helium balloons. You're having a party. So you go to a party city and you buy a tank of helium. And how big is that tank of helium? Oh, it's about this size, like so. About the size of one balloon. Do you only get one balloon out of the tank? You get many balloons. Because why? Because we pack that helium into that tank under great pressure. We force the molecules close to each other. When we open the valve, they escape out into the air or into the balloon, and it is under a different pressure. So they expand to another volume. So gas is what? Okay. So back to liquids then. They have much higher densities because the liquid particles are very close to each other. Gaseous particles very far apart. Liquid particles right next to each other, very close together. And that means you can't compress them very easily. Liquids are not compressible. I think I told you to get an old glass bottle and do that experiment. Also, if you know anything about hydraulics, The whole concept of hydraulics and hydraulic machinery runs on the fact that liquids cannot be compressed. We use liquids to carry out the work action of a hydraulic machine or instrument. Solids have high densities. They have definite shapes, while liquids have indefinite shapes. They'll take on the shape of the container. Both liquids and solids have very small thermal expansion. Gases will expand greatly with increasing temperature. You heat up that balloon and, wow, it gets even bigger. Take a small balloon out on a summer day, put it in the sun, and it's going to expand.
You said
Should it expand?
Heat.
you said liquids and solids have low thermal.
Low thermal expansion. In other words, they don't expand very much at all. They'll expand a little bit, but not much.
What did you
compared to
say
gas.
about the density of solids?
Density of solids very high.
So every liquid that has smell to it has a gas with it.
If a liquid has a smell to it, what we talk about is the volatility of that liquid. And that means that some of that liquid will evaporate. And we'll talk about this. We're going to take a look at what happens if you put a liquid sample into a bottle and what might happen to it. And so we'll bring up the concept of smelling it again in a second. Okay, so why do we have these different states? Solid, liquid, gas, and why do we convert from one to the other? Let's take water, for example. Can I have water in the solid state?
Yes.
Yeah, we call it ice. If I warm it up, will it change into a liquid?
Yes.
If I warm it up further, will it change into a vapor or a gas? Why does it do that? Or how am I able to do that? We know that it takes heat or energy in general to make that happen, but why should that happen at all? The explanation is the fact that there are intermolecular attractive forces. Say what? Now, there are also intramolecular attractive forces. The intramolecular attractive forces are what we've been talking about for the past week or so. They are the chemical bonds that exist. They are the attractions inside of a molecule that result from, in an ionic bond, it's a positive-negative attraction. In a covalent bond, it's the sharing of electrons that leads to an energy stabilization, and we call that an intramolecular force. These are inside the molecule. Intermolecular means between molecules. And so now we're talking about something a little bit different. What are the attractive forces between molecules? Well, let's take a molecule like HCl. Here we're going to see some of our background coming into play. What can you tell me about HCl? A, diatomic. It's got 2 atoms. B, a single bond exists between the hydrogen and the chlorine. Can you tell me some other things about HCl?
It's an acid.
It's an acid. Okay? Perfectly covalent? It's polar covalent. And why do we know it's polar covalent? Because the 2 guys are different. And what polar means is that the 2 atoms involved do not have the same electron sharing abilities. One of them has a stronger attraction for the electrons than the other. Can you tell me in this case which one you think has the greater attraction for the electrons?
The chlorine.
It's the chlorine. The chlorine has the higher electronegativity. Remember, that's the property that we would use to decide this. Chlorine has a greater electronegativity, which means that the electrons hang out more around the chlorine than they do around the hydrogen. So we use the little Greek letter delta, which is that squiggly thing, to indicate partial charge. What we're saying here is that part of the electron has moved over closer to the chlorine. Now we can view this in several ways. If you like thinking about the electron as a hardcore particle, a little BB for example, okay, then we have to talk about time. the electrons are spending more time with the chlorine than they are with the hydrogen. If we're talking about the electron as a cloud, which is often a very good way to think of the electron, not as a particle at all, but as a mist or a cloud, then the fogginess is greater around the chlorine than it is around the hydrogen. In either case, the idea is the chlorine appears a little bit more negative to us. And this sets up what's called a dipole in the bond, a bond dipole, so to speak. Now, if that bond dipole is permanent, it exists, and it does in this particular case, because hydrogen's always different than chlorine, then what if I had a mixture of these guys? Let's put a few more into the picture. Let me put another HCl here. What would the arrangement in terms of those charges be for the HCl, do you think? Positive what? Who? Both of them are positive?
The hydrogen is more.
It'd be exactly the same as the
slightly,
first one.
yeah, positive.
So the hydrogens would appear positive and the chlorines would appear negative to us. Now, what do we know about positive and negative charges? They attract one another. So look, I get an attraction here between the two molecules. And this attraction is called a dipole-dipole attraction, because we've got a dipole in one, we've got a dipole in the other, and the two dipoles are attracting each other. And so here is an intermolecular attractive force that exists in a sample. Now, if I have more HCl's in that sample, which I probably do, then I could have another one here, and will I get the same kind of interaction taking place there? Yes. And I could write another dozen HCl's around here, and we would find that they would all be interacting with each other. So it's kind of like a cocktail party where everyone's standing around conversing, interacting with each other in this mass. And if this is a gas, then they're moving, so they might move out of the realm of one of their neighbors, but they move into the neighborhood of another neighbor, and they have the same kind of interaction taking place. So there are tons of these interactions occurring inside this particular sample of matter. Now, the degree to which something is polar, the separation of charge here varies a lot. Some things are a little bit polar, some things are a lot of bit polar, okay? And so because that varies a lot, and the size of these particles plays a role in this. Does size make a difference in terms of the attraction? Let's think about a magnetic force, very similar to a positive-negative force. Suppose I have an extremely powerful magnet, okay? And we give a young lady in the front row a nail to hold. And when I tell her to let go, she lets go. What'll happen? Clang. It goes straight to the magnet, right? Now we'll give a young lady in the back row the nail to hold. I hold up the magnet like this and ask her to drop the nail. What do you think will happen? Boom, it'll go straight down to the floor. This isn't a cartoon, okay? So why the difference between these two? Same nail, same magnet, different distance. So the distance plays a part in this. And so because we can have so many differences in the degree or the magnitude of the polarity, and so many differences in the sizes that are involved here, we get a lot of different strengths of interaction. And that means most substances don't act like other substances. They have their own set of parameters, and they have their own dipole-dipole interaction, which gives them their properties. What kind of properties? Let's talk about boiling. What do we do when we boil something? I've got water on the stove. It's boiling away. What's happening in terms of those particles?
They're moving really fast.
Water particles that are close to each other, moving real fast, but close to each other in the liquid state, are now being converted into the vapor state, where they're very far apart from each other. So literally, what do I have to do to get these two guys to separate from each other? That's an attractive force. It takes energy to do that. I'm supplying the energy from my stove. The little gas is burning on there, the kettle's hot. That energy is being used to pull the particles apart. Okay? So, if every one of these interactive forces are different for different substances, will every substance probably have its own boiling point? That's why things don't all boil at the same temperature. Because the interactive force, the amount of energy needed to pull this apart, is going to differ from one substance to another substance because of all these parameters that are at play here. How strong is the dipole? How close are they to each other? Yada, yada, yada. Now, there's a couple of special cases, one particularly special case, that we should be aware of. When hydrogen is attached to a highly electronegative element, and there are 3 of them that count. They are fluorine, nitrogen, and oxygen. When hydrogen is attached to one of those guys, the dipole becomes very significant. It becomes stronger, okay? And if hydrogen's involved, let's take my favorite molecule, water. If hydrogen's involved, hydrogen is also the smallest of all atoms. So if I've got 2 water molecules here like this, the oxygen parts are going to be the negative parts. The hydrogens are going to be the positive parts. So I get positive, positive, negative. Is there an attraction between the positive of one and the negative of another? Yes. And because this dipole is significant, because hydrogen's attached to a highly electronegative element, one of these 3, and because hydrogen's so small, it can get in so close, this is an extraordinarily strong type of bond. So much so that we give it a special name. We call it hydrogen bonding. And hydrogen bonding is a very important concept. In this class, what I'll tell you is, if you don't know the answer to a question, change something to moles. Okay? Chances are that's going to work, at least part way. And even if it doesn't, if you change the number of the problem to moles, I'll be so impressed I'll give you a point. Okay? In Chemistry 1152, which deals with organic chemistry, what I tell them is if you don't know the answer to a question, put hydrogen bonding. Because A, it's probably the right answer to the question being asked. And B, if not, I'll be so impressed you remember that. I'll give you a point once during the semester. So, hydrogen bonding is an important concept. It also answers some questions for us. One, it tells us why is the boiling point of water so high? Water is a very small molecule. What's the molecular weight of water? 18 grams per mole, okay? If I take methane, which is natural gas, CH4, it's 16 grams per mole. Methane boils at negative 161 degrees centigrade. Negative 161 degrees centigrade is where it boils.
What is it?
Celsius? You don't know what centigrade is? Wow, next semester. Just a little bit. Okay, ammonia, NH3, 17 grams per mole, boils at minus 33.4 degrees Celsius. Okay. Water, 18 grams per mole, boils at 100 degrees centigrade. It's an insanely high temperature for such a small molecule. Why? Hydrogen bonding. What we have to do is come in here and break these waters apart to get them to go from the liquid to the vapor state. And it takes an immense amount of energy for this tiny molecule to do that. Now, I don't want to give you the wrong impression. Yes?
I thought we tried it. The hydrogen bond can occur between hydrogen and FNO, or just hydrogen?
No. If hydrogen is attached to F, N, or O,
Okay.
then it will undergo hydrogen bonding. Again, from an H of one to the N, F, or O of the other,
But it has to be molecules with those bonds.
it has to be molecules with those bonds. Yeah.
Okay.
Those are the only ones that will work for hydrogen bonding. Yeah.
Just those 3, the hydrogen.
Yes, just those three. So, I don't want to give you the wrong impression. When we're talking about strength of molecule here, I'm giving you the impression this is a very strong type of attraction. And it is. But I don't want to overplay the idea. Let's talk about this bond. The internal bond, the intramolecular bond. This bond is very strong. Let me give you a real life example. Suppose I ask two people to come up here and volunteer for a demonstration and ask them to hold hands. So they're standing next to each other here holding hands. Could I, as energy, come along and put a little weight behind it and get them to break their hands from each other?
Yes.
I believe I could do that, okay? That's breaking the intermolecular attractive force between those two people. I would have boiled them. They would separate. It's like breaking two water molecules apart. Now, we thank one of the people that haven't sit down. We have one person left standing here. Could I, keep in mind I work out, could I rip the arm off the torso of that last person? I believe I could do this, okay? But it's going to take a lot more energy than separating the two hands, right? So that's the difference between an internal bond like this and the bonds we're talking about today between the molecules. They're both OH. Internal, intramolecular. Intra, within. Inter, between.
Between the two molecules.
This is intra, this is inter.
So there's two molecules.
Yes.
Can you say that again, Dr. Bond?
I'll try.
Intra versus intra.
The internal bond that makes up the molecule is intra. Okay?
Internal is intra.
Internal is intra, within the molecule. Okay? Between molecules is inter. Think of an interstate highway. Where does it go? It's between all the states, right? Now think of intramurals sports. They are the ones that are held on a single campus. So, maybe that'll help.
Dr. Braun,
Yes.
right here. Okay. So inter is between like water.
Between two waters.
Inter.
Inter.
Okay, between two compounds.
Between two compounds.
Intra.
Within the
be-
compound.
Okay.
Inside the molecule.
Okay.
Like boiling water to purify it, has anything to do with hydrogen bonding?
Well, the fact that it takes 100 degrees centigrade to boil that water does. To purify it is a totally different thing. That's a biological thing. What you're doing is you're heating it up so that any live bacteria in there can't survive those temperatures, and they die. Okay? So that when you drink the water, it's not going to infect you with something.
So when you boil the water, you break the internal bonds, but do you ever break the intra?
I could, but the intermolecular bond takes 100 degrees centigrade. The intramolecular bond, remember ripping the arm off the torso, takes over 2,000 degrees centigrade to break that bond. So you're not going to do it in your kitchen. You're not going to do it in our lab, okay? But in a special lab that has a high energy source like that, it could be done. But in normal everyday stuff, no, it will not.
So is all of it gonna be related to heating? To break these bonds?
To break these bonds, it's usually thermal energy that we're talking about, so usually heating. Okay, now, are there others? Yeah. We don't get a lot of snow in Atlanta, but when we do get snow, have you ever noticed that even on a really cold day, snow will disappear? Okay, and that's because the sunlight coming down is a light energy source that can actually cause vaporization of the snow going directly into the vapor state. So there's a different type of energy that's involved, but most of the time it's heat that we're talking about.
Okay. I just want to make sure that, intermolecular bond, that's the dipole, right?
Well, careful. Intermolecular is between the two.
Right.
And it's one dipole and another dipole that are attracting each other that creates that bond.
What is?
So when you say it involves the dipole,
What's the dipole? What is the dipole?
a dipole is the term we use for setting up the fact that there are two different charge centers. There's a positive and a negative charge center. So it sets up what we call a dipole or a dipole moment in the molecule. And since that dipole and this dipole are interacting with each other, we call it a dipole-dipole force.
So does that mean that any, I don't know, it doesn't have to necessarily be HCl, that could be a dipole,
Oh, no. Any polar molecule has a dipole.
any pole.
Any polar molecule. And that's why we spent time back when we did shapes to look at a molecule and decide, is this polar or nonpolar? Remember, you had to look at the bonds and the shape to make that final decision. So any polar molecule will attract another polar molecule. Now, what does that mean about nonpolar molecules? Would you expect a nonpolar molecule to attract a nonpolar molecule?
No.
You would not. So why are some nonpolar substances present in the liquid state? Chlorine gas, Cl2, made up of a chlorine and a chlorine. Is there any charge separation here between these two? There's no reason why one chlorine would attract more electrons than the other. This is a perfectly covalent bond, okay? Perfect sharing. So why would it ever form a liquid? Now, it doesn't form it easily. I have to cool it down to low temperatures, which means very low energy. But why would it form a liquid? We can explain this. When we say it's a nonpolar molecule, we are right. But we're talking statistically, okay? We're saying that the electrons are evenly distributed over the picture here. But we're talking statistically. So let's take a snapshot picture. Let's take a photograph at one single instant. Will it necessarily be an even distribution at that point? No. At that particular point, maybe the electrons are more heavily centered on this atom and less centered on this atom. Well, that doesn't sound right. We said they were nonpolar. Okay, 1 second later, this could reverse. And this side is more heavily electroned than this side. And then the next second, they're both even. So over a period of time, if we average those values, what do we find? Totally even, perfect distribution. And that's what a nonpolar molecule is. But the fact remains that at some instant, it could look like this. In which case, this is a little bit negative, and this is a little bit positive at that instant. Now blink your eyes, and this changes. Blink them again, changes again. Blink them again, changes again. But at that instant, if there's a guy next to him who happens to be perfectly even, think of what would happen here. This is a perfectly even distribution. But he sees a positive charge here. What's attracted to positive charges? Negatives. So the electrons that are perfectly evenly distributed here see this positive charge and say, hey, there's a party in town. Let's run over here. And they become a little bit more negative on this side right here at that particular instant. And now look, will I have an attraction between the positive of one and the negative of another? Yes. But blink your eye and maybe it reverses. But still an attraction. Blink your eye again and it's neutral and there's no attraction. Blink your eye again and it happens. So it happens enough so that if I cool it down low enough to very low energies, these types of attractions actually begin to take effect. And as you can imagine, these attractions are probably dependent upon how many electrons I have.
Right.
If I've got more electrons, I can get more on one side, in which case that pole would be a little stronger, right? So I should have some evidence for this. And by God, I do. The noble gases are the perfect example of this, because look at a noble gas. What is it? Is it a molecule? Say no.
No.
It's an atom. Now, what could be more uniform than an atom? Here's an atom, and the electrons are evenly distributed throughout it. But that's statistically speaking. At one instant, the electrons could all be on your right side of that atom. And then the next instant, they're on the right side of that atom. And then they're on the top. And then they're on the bottom, and so forth. Okay, so if we're saying that it relates to the size of these particles, then what should I find for the boiling point as I go down? What's happening as I come down the group? Size is getting larger. Number of electrons increasing. More electrons, more shift, the stronger the effect. Look at the boiling points for the noble gases. Helium, which has only 2 electrons, boils at minus 269 degrees centigrade. This is an incredibly low temperature. You have to realize that there's something called absolute zero. Absolute zero is the temperature where something no longer has any energy at all. You cannot get lower than that in a temperature scale. And that happens at minus 273 degrees Kelvin, or degrees centigrade. So at minus 269, this means that 4 degrees above absolute zero, helium boils. So how are the interactions strong between helium? Strong or weak? They're extremely weak, okay? It takes only 4 degrees to get them to boil away from each other. But look what happens as we go down that group. We increase the number of mass particles, increase the number of electrons, and look at what happens to the boiling points. The boiling points increase in a continuous trend. We can do the same thing with the halogens. Look at fluorine, chlorine, and bromine. Okay? Minus 187, because it's small. Get a little larger, minus 35. A little larger still, now we're up to where bromine is a liquid at room temperature. Okay? It's going to take temperatures higher than room temperature in order to separate the bromines from one another, because there's some strong interactions taking place there between them. This type of bonding, this type of attractive force, which has a name. This is called a dispersion or a London force.
Talking about chlorine?
Well, the type of nonpolar interaction. Doesn't have to be chlorine, it could be any nonpolar molecule. Okay? London was the name of the scientist who came up with the idea. So that's why they're called London forces. Dispersion's the more general term.
So any non-polar and non-polar.
2 nonpolars will interact with each other through London forces. And that's why we could liquefy them.
What about hydrogen?
Hydrogen? Who's talking? H2?
Yeah.
It boils at about 20 degrees Kelvin. But remember, hydrogen's not an atom. Hydrogen's a molecule. So even though it has 1 less electron than helium, it is a 2-atom system. And so that gives it a little bit more chance to have the electrons shift around from one side to the other. So it boils at a low temperature. 20 degrees Kelvin is certainly very low if 0 is absolute 0, but it's not as low as helium. Hydrogen, yeah. But it's got to be pretty cold. Helium can be a liquid. Helium can be a liquid at under 4 degrees Kelvin. It's a very dangerous substance to be around. You don't want to play with liquid helium unless you know what you're doing, but it can be liquefied.
So why is C3H8 so cold?
So cold?
Yeah, okay.
It's not. If you have a bottle of propane on your deck, okay, and you're not using it, is the cylinder hot? Cold?
I mean, when it escapes.
When it escapes, okay, there's a physical chemistry process that when gases expand, okay, when they go from a condensed area to a liquid area, they absorb energy. And if they absorb energy, then like the flask that I had the other day, what happens to the surroundings? If the system absorbs energy, it pulls it in from the surroundings, so the surrounding temperature drops. It gets cold.
Can you say it one more time about gases expanding and absorbing?
When gases expand, they require energy. So they get that energy from the surroundings, and that means the surroundings cool down. So when gases expand, temperatures around them drop. So when your propane tank is on, and you're burning the propane, that cylinder should get colder. Yes? Yeah, it's the shifting, the temporary shifting of electrons in a nonpolar system. Boy, that sounds good. The temporary shifting of electrons in a nonpolar system. And so that sets up a intermediate or a temporary dipole, which then can cause some attraction.
Dr. Vaughn,
Say it again?
Temporary shifting of electrons.
In a nonpolar system.
in this sense, when we're speaking about polar and non-polar.
Yeah.
For non-polar, are we talking about the fact that they have the same charge,
No?
like the same negativity? I thought that was the
Yes.
equal sharing of electrons.
Yes, but you're confusing two things. That would be the case if you're looking at just the bond.
Okay,
But then remember, we also looked at the molecule. And in a molecule, could we have polar bonds but a nonpolar molecule?
polar bonds, unequal sharing.
Okay?
Okay.
Bond, polar, nonpolar. Very easy to answer. Are carbon and oxygen the same atom?
No,
Then you say polar.
polar,
This is polar.
polar.
Polar. But the molecule is nonpolar because the two are pulling in opposite
And
directions.
they share
Remember
the
chair?
same equal sharing. Okay,
And so
So
we
we're
end up
looking
with
at
an equal sharing overall, even though locally that's not the case.
okay, gotcha. So with noble gases only, as the mass increases, the boiling point.
No, not noble gases only. That'll hold true for just
Okay.
about any type of thing. We
Okay.
saw it for the halogens, fluorine, chlorine to bromine. As the mass increased, so did the boiling point.
Okay,
We will see it for, if you go on to Chemistry 1152, I don't think you are, but
1211.
you're going to, she's going to 1211. That's why. I'm not dissing her. I'm not dissing her, sorry. Those that go on to Chemistry
Even worse.
1152 will
1211.
look at organic molecules, which are nonpolar molecules, and the basic rule is the bigger the molecule, the higher the boiling point.
Okay, that's what I was thinking.
We're good?
I got one more.
Yeah.
About the dispersion forces,
Right.
so the temperature has a lot to do with that. It can't always happen.
Well, these are weak forces, okay? This is a stronger force. This is even stronger, okay? So, how do I break them apart? I'm going to break them apart by using heat. So, in which case will I use the least amount of heat to get them broken apart? In the case where they are the weakest. In which case will it take the most amount of heat to break them apart? In the case where they're the strongest. So that's how the heat's related to what we're talking about. Now, physical substances have lots of interactions that can take place between them. And we have a lot of terms for these changing of physical states. Like we're going from a solid to a liquid or a liquid to a vapor. We have terms that describe that. So I have a slide here that actually describes that for us. And so we'll take a quick look at it. And some of these terms you will recognize. I think there's a couple that you will not recognize, and that's okay. All right, we'll just go for the ones that we know, and you can put it in perspective as to what we're talking about here. So clearly you can see the slide that describes these things in terms of three physical states. We've got the solid, the liquid, and the vapor. It's coming on.
Yeah, it's coming.
Okay, squint and you can see it. So we have solid, liquid, and vapor. These are the three physical states. And they're kind of represented on this slide as a hierarchy in terms of energy. Which one would have the lowest amount of energy? Probably the solid. Highest amount? Probably the vapor for a particular substance. Now, we have what we call transitions, moving from one to the other. So what would we call going from a solid to a liquid state? We would call it melting. And there it is right there. How about if we were going from a liquid to a solid state?
Freezing.
Freezing. Okay? For some substances, like water, this happens at a particular point, a particular defined temperature, 0 degrees centigrade. And so what's the melting point of water? Melting. I just told you.
Melting point of water.
Melting point of water. 0 degrees centigrade. Thought I just told you. What's the freezing point of water? It's 0 degrees centigrade. It's exactly the same. The difference is the direction you're going. That transition takes place at the same point. Now, going from a liquid to a vapor, we call it
Evaporation.
evaporation. Going from the vapor to the liquid, we call it
Condensation.
condensation. In fact, we use the term condensation to usually refer to the end result. If you come out on a cold morning and find your windows all wet, what are you thinking? Oh my God, condensation has occurred on my window. Well, condensation was the process by which the vapor, water in the vapor state, was converted back into a liquid, and it does so on the coldest objects, which is usually the glass or the metal of automobiles, rather than the brick on the side of your home or whatever, which holds a little bit more heat for a longer time. Now, in some cases, it's possible to go directly from a solid to a vapor without going through the liquid. Here's a term I don't know that you'd be familiar with. This is called sublimation. We sublime something. Can you think of a substance that would do this? Dry ice, perfect. Dry ice is frozen carbon dioxide, and it goes from a solid state directly to a vapor state without going through the liquid. Thus the name dry ice. It stays dry. Okay. If we go from the vapor state back to the solid directly, we call it depositing or deposition. In next semester, those of you that go on to Chemistry 1152, in the laboratory, you're going to isolate caffeine from tea. And to get the caffeine, we extract it with a solvent, but it's kind of dirty at that point. So we clean it. And we clean it by subliming it. Caffeine will sublime. You put it on a hot plate, you heat it up, it goes from the solid state into a vapor state. You put a cold receptacle on top of that, and as the vapor molecules come up, they get cold and they redeposit back again. But all the impurities stay at the bottom, and you isolate pure caffeine from that mix. All right, questions? No, we understand it perfectly.
What? That's a lot of time to see her. Come see her.
So, let me take a bottle, and I want to put some liquid into that bottle. I don't care what the liquid is. Sometimes it's to our advantage to talk about water because we're so familiar with it. But realize that if we do lapse into talking about water here, it could be any liquid. It could be mineral spirits, or it could be an oil of some kind, or whatever. I'm going to put a cork on the bottle to close off the system so that everything stays inside the bottle. Now, at time 0, all I've got is liquid particles here. What are they doing?
They're moving around.
They're moving around, right? We did the experiment with the food coloring that shows they're moving around. And as they move around, they bang into each other. They bang into the floor of the bottle. They bang into the wall of the bottle. And there's a guy on the surface here, minding his own business, that might all of a sudden get hit, bam, hard from behind. What if that collision gave him enough energy so that he now broke those intermolecular attractive bonds and entered the vapor state? Possible? Very. So now we've got a particle in the vapor state. What's that particle doing?
It's moving around.
Moving around. He's going everywhere, banging into the walls, banging into the cork, maybe banging into the surface of the liquid. And when he bangs into the surface of the liquid, maybe he loses some energy and gets recaptured and now returns to the liquid state, right? Okay. At time 0, when I just put the liquid in there and I have not allowed any of them to vaporize yet, how many vapor particles do I have? 0. So what's the chance of a vapor particle going back to the liquid state? 0. There aren't any, so it's got to be 0. But is there a chance in my sample that some of the liquids could become vapors? Just because the liquids are moving around, so that could happen. So there's going to be a certain rate at which particles move from the liquid state to the vapor state. And it creates a vapor particle. Now, as soon as I get a vapor particle, does it have a chance of returning to the liquid state? So I've improved that chance. But it's probably pretty small because I've only got one particle at that point. So if they're going into the vapor faster than they're leaving the vapor, what's the net effect here? I'm going to build up vapor. And as I build up more vapor, what happens to this chance or probability that they're going to return?
It decreases.
It increases. And do you think I could increase them to the point where now all of a sudden they're equal? And every time, statistically speaking, every time a liquid becomes a vapor becomes
A liquid.
a liquid. This is a special system, circumstance, and we call it equilibrium.
That's easy.
We say that our system has reached equilibrium. And if this bottle is closed and we measure the liquid amount in there, that amount will never change under these conditions.
So it's the equal amount of, like, I don't know how to say it in words, but the equal amount of how vapor can go to water and water can go to vapor.
Sort of. It's what we say is there's an equal rate of exchange. Does that work for you?
There we go.
Equal rate of exchange. Now notice it does not mean equal amounts of vapor and equal amounts of liquid. That's not true. But there's an equal rate of exchange between the two. Okay? And so we have established equilibrium. Now, if I were to put a device on the side here that could actually measure what's called pressure, the amount of vapor that's in there, because those vapors are moving around, punching the wall, punching the cork, punching my little device there, and they measure a certain pressure value, and that's called the vapor pressure of my substance. And so liquids all undergo this process. They will all vaporize to some extent. Okay? Now, what's going to make one vaporize more than the other? What's holding them in the liquid state? Intermolecular attractive forces are holding them. So if I do things that change those forces or change the interaction between those forces, then I'm going to get a different result. But let's say I've got the same temperature for two different bottles, but I have a different substance in there. Will they have different intermolecular attractive forces?
Yes.
So will their vapor pressures be different?
Yes.
Yes. So something that has very weak intermolecular attractive forces is going to have a very high vapor pressure, and vice versa. If something has strong intermolecular attractive forces, it has a relatively low vapor pressure.
Vapor pressure is PSI?
No. It could be measured in PSI, and it certainly could be. Okay, but I don't think it's the PSI you're thinking of. What you're thinking of is what's called the atmospheric pressure, which we're going to relate this to in a minute. Okay, but PSI is pounds per square inch. It's a unit for measuring pressures. So yes, it could be used for vapor pressures. Okay, in the laboratory, we're probably going to use it in millimeters of mercury. So if you've done the lab this week, the atmospheric pressure lab, you know that we measure atmospheric pressure in millimeters of mercury. Or you could do it in inches, if you were a weather person on TV. Since Americans hate the metric system, they record the barometric pressure in inches, okay? I'm not sure anybody understands that any better than if it was recorded in millimeters, but that's what they do. All right, what would happen here if I remove the cork? Now my vapors have another option. Instead of just hitting the walls or hitting the liquid or hitting they could go through the opening in the jar. And if they go through the opening in the jar, for all practical purposes, we say they're gone. They're not coming back, okay? Because if it leaves that jar, if it leaves this bottle to enter this room, what's the chance or likelihood it's going to find that hole again to get back into? Probably not very good. So, if I open the cork, then I lose some vapor particles. If I lose some vapor particles, what happens to this return rate? It goes down. But this rate stays the same. And if this rate stays the same, but this rate stays down because I've got molecules that are continuously escaping, is there a net effect in my system here? The liquid will evaporate. And eventually, the liquid will be gone. Totally. Unless I were able to reach an equilibrium with the room. If I was able to establish an equilibrium with the room, then the room becomes my new bottle and the liquid would reach an equilibrium with the room. Okay, anything else that might affect this? What if I were to heat this sample? What does heating the sample do to the liquid?
Evaporates.
They're going to move faster. If they move faster, do they hit harder?
Yeah.
If they hit harder, is it more likely that they will be shoving guys into the vapor state?
Yes.
So my increase rate is going from liquid to the vapor, okay? Now, let me put the cork back on real quick. At that instant, I'm not at equilibrium. So the net effect is to make more vapor. But as I make more vapor, I increase this rate. More vapor, increase it some more vapor, increase it some more. Will it reestablish equilibrium if I have the cork back on there?
Yes.
Yes, it will. But now there's probably more vapor.
It's going to cause some
And
problems.
so what happens to the vapor pressure as the temperature goes up? It increases. So as we increase the temperature, the vapor pressure increases. Now,
As we increase.
as we increase the temperature, the vapor pressure increases. Now, all around us are gases. We know that because we're breathing air, and air is made up of gases. So, let's go to the beach. These are waves. Okay? I'm going to put a guy on the beach. He feels an effect due to those gases. There are approximately 600 miles of gaseous particles, pushing down on his fragile little frame. And that creates a pressure. And we call that the atmospheric pressure. The atmospheric pressure. Now, if there's a mountain next to the beach, and we put a guy on top of the mountain, does he feel the same pressure that the guy on the beach feels?
No.
No, because why? He's got molecules pushing down on him, but the guy on the beach has all those molecules, but the guy on the beach has extra molecules pushing down on him that the guy on the mountain does not have. So he feels a smaller or lower atmospheric pressure. Now next to the mountain we have a valley.
You're messing up my picture.
I better use a girl. Okay? Does she feel the same pressure that the guys feel? What's her pressure? Greater. Because she's got all the molecules the guy on the mountain has, all the molecules that the guy on the beach has, and more pushing down on her. Okay? Now, interesting thing about heating. Let's not heat with the cork on. Interesting thing with heating. I increase the vapor pressure. I heat it some more, I increase the vapor pressure. When my vapor pressure reaches the atmospheric pressure, a phenomenon occurs. That phenomenon is called boiling. So boiling takes place when the vapor pressure of my liquid equals the atmospheric pressure. Now remember, the vapor pressure of liquids are all different. So they all get to the atmospheric pressure at a different temperature. Therefore, they all have a different boiling point.
So what if there's
When the
Equilibrium.
vapor pressure equals the atmospheric pressure. Now, does that mean that if we did an experiment on these 3 locations, that we would get the same value for the boiling point of water? No. Why?
Because the atmospheric pressure is higher and
The
lower in different
atmospheric pressure is
locations.
different. And so I'm going to reach that local value at a different temperature each time. Okay? And how can we stand here and say the boiling point of water is 100 degrees centigrade? That's a bunch of crap. Okay? Because it's not. But it is if we define the pressure to be 1 atmosphere. So if we say the guy on the beach experiences 1 atmosphere pressure, then that's where we define the boiling point of our sample, our water. Now let's quickly talk about food. What if I'm making food? Let's say I'm making boiled eggs, soft boiled eggs, and I love my eggs done 3 minutes. The perfect soft boiled egg for me is 3 minutes. So I asked the guy on the beach, start a fire, boil some water, and make me 3-minute eggs, okay? He boils them for 3 minutes, and they are perfect. Now I go up to see my friend on the mountaintop. We have to build a little ledge here. Is he going to give me the perfect egg if he cooks his eggs for 3 minutes? What should he do? Should he cook them longer or shorter?
Longer.
Remember, he's cooking at a lower temperature. So he should cook longer to get the same cooked consistency for my eggs. Okay? Because he's not putting as much heat in there as the guy on the beach was. Now, if I go down to see my lady friend in Death Valley, is she going to cook them longer or shorter? Shorter. She's going to cook them shorter. So do food packages sometimes have altitude directions on them?
Yes.
Because this can affect the food production that we're talking about. All right, why don't we stop here? We're trying to finish this chapter up on Monday.